All right, hey you guys, John Britt here. We're gonna finish up these oxide properties that I was doing yesterday. And I'm gonna do my best once again, but of course, you know how it goes. Sometimes you mess things up. I made one mistake. I said potassium favors copper blue in reduction, but that's not true. Copper in reduction will make reds. It was supposed to be iron blues, so blue celadons. Okay, that's not the end of the world because you're going to be reading in the book about all this stuff anyway because it's massive, and you want to be able to read in the book so you can apply it to things that you've seen on your own or your friends' work or you see online, and that way you can connect it all together and start creating your own stuff, okay? So right now we're going to do, we've done the fluxes, the refractory glass former, some boron and phosphorus, plant and bone ash for phosphorus. So we're going to do opacifiers, and then we're going to do these colorants. But you can see we have quite a few, so we have to go quickly as always. That's the name of the game here. But like I said, you're going to spend a bunch of time looking things up on your own. In my book, I think around page 29, 30, 31, something like that, I have all of these and a whole bunch of things about each one. I'm not going to be as tight to this property deal because the colorants, the main thing we're concerned about is, you know, what colors we can produce with them. All right, so let's start with tin, titanium, and zirconium. These are our opacifiers. And opacifiers, if you do a base glaze with nothing in it, it's generally transparent or semi-transparent, white. But if you start adding, if you want them to be not see-through, then you're going to add something to make them opaque. That's opacifiers. And these each have different qualities. Like tin, this is SN10, titanium, and zirconium. This makes off-whites, this makes refrigerator whites, and this makes milky, streaky whites. So you get different effects from different opacifiers, and you can also use them in combination. So you can use like 3% of each one, and you get a much different look than 9% of one. Okay, so we'll do tin first, and that melts at, tin oxide, that melts at 2102, and it has high coefficient of expansion, high surface tension, high viscosity, no volatilization, not really that toxic. It's got it's a good color response. It makes nice off-whites. And so there's, in the olden days, Maiolica used to be called tin white because they used tin to make it look like porcelain, to imitate porcelain. So they made this white surface and then they would paint on it. So that's like Delft ware and Maiolica, and anyway, there are a whole bunch of types of it. It can make pinks a lot because copper will flash, chrome will flash, and they'll turn tin whites pink. Oftentimes people will fire their, like a tea bowl in a sagger, which is just a bowl, and they might paint the side of the sagger with chrome green and then put a tin white tea bowl in there and it'll flash it pink. Okay, let's see, the source of it is just basically tin oxide. Okay, so let's do our next one, which is going to be titanium. And that makes milky, streaky whites. And so one most common thing you probably know is rutile. That is iron and titanium, and it makes that milky, streaky effect that's oftentimes in floating blue and glazes like that. So this one has a melting point of 3326, and it is medium surface tension, high viscosity, no volatilization, not really too toxic. The reason I just say not really, because as you know, toxicity is super complex, and you can't say yes or no. But we have to say something in ceramics because we're forced to deal with it. But it's like when I start talking about these colorants, all all of them are toxic, pretty seriously toxic. Iron is the least toxic of all of them. But anyway, that's the deal. But if you are sensible in your lab and you aren't breathing a bunch of dust and you're not getting it in your cuts and you're not getting it all over your hands and you're not breathing in the fumes, then it's very, very safe. Okay? So I'm going to say no on toxicity. Color response is milky, streaky, flushing kind of effect on the surface. So as always, you can use, I forgot to tell you, tin, normally you would use at like 4%. Zirconium you're going to use at 8%, so it's twice, you need twice as much to get the same opacification. And zirconium you can use, titanium you can use in small amounts, 2 or 3%. You can turn a copper red from a red to a blue by adding 3% titanium. You can add 5%, 10%, 20%, turns kind of yellowy. So, and unmelted. So that's what you're dealing with, is how much am I adding to get these effects. All right, main source titanium dioxide and rutile. All right, let's do our next one is going to be, let's do it here. Okay, so this is zirconium oxide, and that's generally in the form of zirconium silicate. They sell it as zirconium silicate, so that's Zircopax, Zircopax Plus, Ultrox, Opax. There's many former names of things, and the more, well, they say Zircopax and Zircopax Plus is just a finer grind of Zircopax, so it opacifies better, slightly better. It melts at 4892. That's super hot, and so I know Tony Hansen has a kiln wash recipe that is like 4 Zircopax, 1 kaolin to suspend it because it won't melt. It's got such a high melting point. Okay, it's got a low coefficient of expansion, high surface tension, high viscosity, does not volatilize, not really toxic. Now, as you know, I don't know if you've forgotten already, but surface tension, it means it could cause crawling. Viscosity means very thick. Coefficient of expansion, high will be crazing and low will be the opposite, towards shivering. But this will not shiver, but it's a low coefficient of expansion. So sometimes when you add Zircopax to a glaze, and that's just barely crazing, it'll stop the crazing. And presumably that's because it's a low coefficient of expansion, depending on how much you add, or that it's adding silica to the melt with zirconium silicate. I'm not sure of all the reasoning behind this, but that's the idea. Okay, so let's now do our colorants. So we're going to start, and I've listed them up here. There's many valences of these things. So if you're getting iron, not only are there many sources of iron, because there's iron is in almost everything, but there's many like FeO, Fe2O3, Fe3O4, like that. So there's many states of iron, and what we do when we fire is we change those states. So if we start off with Fe2O3, we can see that's an R2O3. We can see that's refractory. Generally, we're going to predict that. Now when we reduce it and we make it FeO, that is an RO. That's going to act like a flux, and it can be many states in between. What can happen with oil spots is when you put iron in there and you heat it up, it will naturally want to change its state as it gets above like 2200 degrees. It'll start to let go of an oxygen and become a simpler form, and that causes bubbling, and then we can get oil spots that way. So all the things we're heating, like I said before, we're heating up sodium carbonate and driving off the gas, calcium carbonate and driving off the gas, magnesium carbonate. So we're always driving off these gases and changing the states of our material. Okay? let's see what I'm going to say about this one. It melts at about 2849. It has, what am I going to say here? It's not really that toxic. The main states are going to be red iron oxide, which is that. This is black iron oxide. This is yellow iron oxide. So it's got a water associated with it. So you can see just from looking at these formula that this is going to be the strongest because it's only got one oxygen. This essentially has 1.5. This has 1.5 plus water. So for every gram of material, you're getting less and less iron as you go from here, here, or here. Okay, sources of it would be, you can get natural iron, you can get Spanish iron oxide, which is bacterially ingested. You should read about that, it's very interesting. Yellow iron oxide, yellow ochre has got clay associated with this also. Let's see, what else we got? Oh, and then the colorants that you get from it. You can make blues in reduction, blue-green, amber, Temaku, that's browns, iron spangles, that's with like 20%. You can do goldstone, which is a crystalline form of an iron glaze. Aventurine, which is a sparkly other crystal form also. I think that's it. Yeah. All right. So that was a big one. Now we'll do copper. Let's do copper. Copper oxide, and it melts at 2098, but it starts to break down from copper carbonate at about 982, and so it lets go of an oxygen from the carbonate form, CuCO3. So that'll restructure, and that's why you get some bubbling with copper sometimes, especially if you use it with lichen glazes that are very stiff. You'll see little holes still in there from where that left. It does volatilize. It is toxic, yes. Like I said, almost all of these are very toxic, the colorants. It will make greens, red, pink, blue, blue-green, many forms of like, just many shades of green. So you can add a little bit of iron, a little bit of cobalt, and just shift it all around. People love that. It makes black, and it makes metallics, and then copper yellow is another unusual one you can get. Okay? One other thing about it is you also get copper sulfate, and that's a water-soluble form. There's a whole group of sulfates that people use to do watercoloring on porcelain, which is a pretty cool thing. But those you want to make sure you have gloves on because it can go through your skin. And red copper oxide is often used in raku to make the matte iridescent-y kind of bluey, greeny, yellowy, flashing stuff, the flashing matte glazes in raku. And with that one, you have to add soap to the red copper oxide because it's got a surfactant on it that doesn't allow it to get wet. And so the soap helps it to go into suspension. All right, we'll do cobalt. Okay, so cobalt, very nice colorant. And it I think 1472 is where it melts, and it decomposes. And what it can do is cause splattering on your other work. And so you want to go slowly sometimes in the early stages of the firing, or you get blue spots on everything. The form would be black copper oxide, copper carbonate. That's the most common one to use because it goes into a glaze melt really well. Same with cobalt carbonate, cobalt sulfate, cobalt oxide. But the same thing with copper is you usually use the carbonate form because it goes into the melt better. And with copper, sometimes you get specking from black copper oxide. But let's go back to cobalt. It is toxic, yes. The color response normally gets blue. But you can also get blue-green with it, or green if you slow cool. And that is from having titanium in there. Titanium or rutile in your glaze, and you add cobalt, you'll get a green. That's the only time. I think that's about it. Oh, when you get it with, sometimes in crystalline glazes, you get, it's mined in association with nickel. So sometimes in nickel, they can't get out all the cobalt. So there'll be a little bit of cobalt left in there, and that's why you get an amber field with blue crystals, because that tiny amount of cobalt is the first to go into the crystal. Okay, so now we're going to do manganese. I hope I'm doing well here. The problem is with doing these by myself in this room is there's nobody talking back to me, so I don't know where I'm at really. I'm just kind of charging forward. So we'll find out tomorrow probably. So we got manganese dioxide. It melts at 1976 approximately Fahrenheit is where it decomposes, is what I meant to say. It decomposes and gives off gas. So sometimes what happens is you'll get bubbling also with this. You'll notice in your glaze, you'll see pinholes, or like I said in the lichen glazes, sometimes you'll see remnants of where the gases came out. Okay, it volatilizes, yes. Toxic, yes. Color response, it gives you browns, blacks. Black is often a grouping of oxides like chrome, iron, cobalt, nickel. That's the way you produce blacks. You oversaturate it with all these colorants. You can get purples and manganese yellow, and then metallics and gold type colors. All right, so now we're going to do chrome. Chrome, toxic, yes. And it has a pretty high melting point, I think. I should have done nickel neck, but it's 4109. And that is very hot. It does volatilize, so it can flash pinks. You like to fire it out, have good ventilation, or have it outside. That movie, Aaron Brockovich, was hexavalent chromium is very dangerous, and it was in the groundwater. Also, when we get our chrome oxide from the store, it's not necessarily just one pure valence. It's multiple ones in there, and we never know. And that's why I like to be pretty safe about handling these materials. Okay, it makes a bunch of different colors. It makes black, greens, many shades of greens like forest green, chartreuse, lime green, all depending on the other oxides in the recipe. Makes pinks, and the sources would be chrome oxide or iron chromate or potassium dichromate. All right, let's do nickel. We'll go back to nickel. Nickel oxide, so that is, it melts at 3614 about. It is toxic, and it has a fume, yes, and yes, and it makes, it's a difficult material to use. It becomes unstable above 2194, and so it's hard to control this material, but you can get some really nice colors with it. You can get blacks, browns, grays. They have like 0.5 nickel in there. You'll get blues and yellows, pinks, and it's good in crystalline glazes. Okay, so now we're on to vanadium, getting down to the wire here. V2O, vanadium. So this melts at I don't really use this. A lot of these I don't use a lot. They're usually, you get yellows with this. It's got a toxic, I'm not sure if it has a fume. I'm going to say yes, but I'm not sure. I know it's toxic. It is usually in stains to make yellow. And so they mix it with like tin or zirconium, and they get nice yellows with that. And by they, I mean you, people like you. All right, so then, according to our list, all we have left is going to be the lanthanoid oxides, gold, silver, which I'm not going to say much about. Those are in lusters, and usually you can do silver nitrate lusters. You can do paint on gold lusters you can purchase or make yourself. And then I have molybdenum and tungsten. Well, I'm not really going to talk much about them. They can make golds also and iridescent-y kind of colors. You know, there's a lot of other things we could talk about. I didn't talk about bismuth. That's a very good flux. But I'm just talking about the main things that we would normally work with. Okay, so the last one is going to be praseodymium. It melts at 1710. Okay, and I said the lanthides are neodymium, erbium, samarium, etc. There's like 15 of them, and they're called rare earth elements. And they don't really use them too much because they're very expensive, but people do, and they make some beautiful colors, and they make different colors in different light. So you can have it be pink here and bluish over there, and like fluorescent or LED or sunlight, etc. So some people like that. Let's see. It's very toxic. It makes I don't know about volatilization, and I'm not going to talk about each one of those. You'll have to look those up. David Peer did a nice article a few years back in Ceramics Monthly about recipes for sort of like celadon-y pinks and blues and stuff with rare earths. So that would be something to look up in Ceramics Monthly. Mainly you can also get yellows, but I usually just buy stains to get this stuff. Okay, I think that might be all that we have. And then next time what I'm going to do is we're going to do like practical examples. I may take a glaze and break it down to what's in it and like just show you ways that you could at home pick one glaze, deconstruct it, reconstruct it, change colorants, and learn all about that glaze, which in the long run doesn't really matter about that glaze, but it'll inform all glazes. So you learn what silica does, you learn what zinc might do in this glaze, because we don't just have 100% of one thing in a glaze. We'll have multiple types of oxides in there. So we have to be able to look at a recipe, sort of predict what it'll be, or we can make our own recipe. So we're going to do that next time, and I hope you go home and read some from the book. It'd be super good.